The next question I'm going to be doing for you guys is question 23. It says boxes A and B are in contact on a horizontal frictionless surface. Box A has a mass of 20 kilograms. I'm going to go ahead and notate that on the picture. 20 kilograms, and box B has a mass of 5 kilograms. There we go. A horizontal force of 250 newtons is exerted on box A. What is the magnitude of the force that box A exerts on box B? So in order to handle this, you're going to have to create some free body diagrams. And this one's nice because there's no friction, but sometimes if there is friction, it's going to get a lot more complicated. And we'll see that in question 26. But first off, we're going to do a free body diagram for object A. Actually, I'm going to draw that A with a circle. That's object A. Sorry, it looks like crap. We need to draw the forces that are present on it. And all of the forces are going to be based on either gravity or things that are in contact with the A. So first off, you've got force of gravity going down, which I'm going to write as mg, which should also be 20 times g. And then for the contact between the table and box A, you've got a normal force that counteracts that mass and gravity, holds the box up. Then you've got a force applied. This is not technically an ideal free body diagram. You're supposed to have all the tails on the object itself. I'm not doing that because it doesn't make sense to me. That's what AP wants, but you can draw it however you like. And then we're also going to have some force from B, because B is touching A. So that's the force of B on A. Then for object B, you've got some really similar stuff. You've got mg, but this is mass of B this time. You got a normal force from the table. You've got the force of A on B pushing B. Now, once you get to this point, there's one thing you got to realize, and it's that these two forces, force of A on B and force of B on A, have to be equal in magnitude. They're going opposite directions, but they're equal in magnitude because that's Newton's third law. So that's a constraint that we have. Now, at first glance, this problem is seemingly simple, complex, because there's one more restraint you've got to see. If we're pushing box A and box B, unless B goes flying off and A stays where it is, which can't happen, then they're going to be moving at the same rate. So they're going to have the same acceleration. That's a subtlety that's hard to see. Acceleration is the same. So we're going to have to use that constraint in Newton's third law to calculate the force of A on B based on their masses. So we can go ahead and look at several different things. And the first is all of the forces on A. The force on A happens in two directions, X, which we'll call horizontal, Y, which we'll call vertical, right is positive, up is positive. So in the X direction, or the I direction, on A, you've got 250 newtons going in the positive direction minus the force of B on A. That's happening in the I hat direction. And then for J hat, in the Y direction, you've got Fn minus mg. And mg, we can go ahead and plug in. For A, the mass is 20. So 20 times g. I'm not going to plug in the g because I don't really want to deal with, it right now. And those are in the J hat direction. Now I'm going to take those and move them over a little bit. Because due to Newton's second law, we know this is mass times acceleration. And the mass is 20. So I'm going to make that 20A. Now the force on B, we've got a free body diagram for that as well. In the X direction, the only force you have on B is the force of A on B. F, A, B. And it's in the positive direction, I hat. Then for your other direction, for your Y direction, you've got Fn minus 5 G, J hat. equals, not 20 times a, mass times acceleration, which is 5 times a. So what you've got here is a system of equations. And I'm going to take that system and I'm going to transfer it to the next page. That way we can work with it a little bit better. All right, now here's my system of equations on kind of a cleaner space, but there's something that we have to fix a little bit, and it's because it was poor notation on my part and I didn't really mention it a second ago. So our acceleration here, oh, sorry, didn't mean to wiggle that. The acceleration here has a constraint. We know that when you push it horizontally, like since it's only being pushed horizontally, it's not falling up or down, our acceleration is only going to be in the I direction. So we're going to have some sort of acceleration in the I direction and 0 acceleration in the J direction. Oh, that was bad notation. 0 in the J direction. So I'm going to change that over here. For our A's, I'm going to input this notation. So instead of A, oh, it won't let me get rid of it. Oh, now it's gone. You'd think I would have learned to use this program after so long. Okay, so our acceleration is 20 in the 20 times A in the I direction, because 20 is still the mass, plus 20 times 0 in the J direction, but that's still just 0. But we're going to leave it there as a placeholder. And then we get the same thing, but times 5 in the I direction, 0 in the J direction. So now this becomes a kind of disgusting system of equations. Now, the acceleration and the force that we need are both in the X direction. So our Y direction stuff, while it's generally important for most questions, is not for this one. You could solve for the Fn by setting each one equal to 0, but we're going to get rid of those because we don't really need them anymore. Everything's just going to cancel out to be 0 there, and therefore we don't care. So we're going to reduce this a little bit, set it equal to 20 times A in the I direction and 5A in the I direction. So now we're just going to have to solve that. I'm going to drop the notation because now everything's in I. So it's just going to be 250 minus force of B on A equals 20 times acceleration. Oh, I wrote it too. 20 times A. And force of A on B equals 5A. Now we had another constraint back there on the free body diagrams. It said that the force of A on B and the force of B on A had to be equal in magnitude but opposite in sign. Now we have already taken care of the opposite in sign thing because when we plugged them in to our forces equations, we made B on A positive and A on B negative. But we know they are the same magnitude, so we can plug them in as the same number. So here where I have f of A on B, I can put f of B on A since we know they are equal. So now we just have a system of two equations, and you could solve this for either A or FB of A. The question wants F, the force of A on B. So we're going to find that. The way to do that, the way I would do it, is multiply each of these by a 4. That's bad notation, but you get 250 minus F of B A equals 20A, and then you've got 4, force of B on A equals 20A, and then you can subtract this whole equation. I don't have enough space, so I'm going to write it over here. You get 250 minus 5, force of B on A equals 0. And to solve that, you get 250 equals 5 times force of B on A divided by 5 on both sides. 50 equals the force of B on A, which is also equal to the force of A on B. That's your whole question. Now there are actually way shorter ways of working that, a lot shorter, and you might know some of them. But I'm trying to get you used to the notations that we're going to have to be using for the more complex problems and the actual problem solving steps. drawing the free body diagrams, adding up the net forces, evaluating things from a vector's perspective, because that stuff's going to be required for our harder problems. This is like a run-of-the-mill base level kind of problem. When we get to the ones with calculus, you're really going to have to know your stuff as far as the steps for really solving force problems. So feel free to use the shortcuts when they work, but you're also going to have to know how to grind it out when they don't work.